Welcome everyone. My name is Kristen Mulheron and I'll be moderating GoProto's Office Hours discussion today. This is the inaugural Office Hours event with a focus on 3D printing versus injection molding, which one and when. So to get things started, I'm going to introduce our panelists today. Today we have Mark Basinger. He's the Director of Western Sales at GoProto. We have Jesse Lee. He's the President at GoProto. And we have Jonathan Wilkie. He's the Director of Eastern Sales. So as a bit of background, Mark has a background in both 3D printing and manufacturing industries with a proven track record in providing manufacturing solutions for Fortune 500 companies and startups. He helps his customers with understanding the product development cycle and how to implement the appropriate resources at key phases. He's passionate about providing custom manufacturing solutions with a special interest in time compression, cost effectiveness, and quality. Jesse's the president. He is our 25-year student of the rapid manufacturing space. He's been a part of the incredibly diverse product development programs from early prototyping for products like the iMac in the 90s through high volume additive manufacturing for complex projects like HP's 580 color printers. Listening to client partner needs, utilizing the latest and greatest array of manufacturing technologies, and working with the best people in the product development and manufacturing community is what Jesse finds most exciting. Jonathan Wilkie started his career as a mechanical design engineer utilizing Pro-E, designing plastic parts, heat sinks, and sheet metal parts. He has experience running both 3D printing production equipment, including SLS, SLA, and FDM technologies, as well as designing parts for injection molding as part of a team of tool and die engineers and molding engineers. So, welcome everyone.
Thank you.
Hi everyone.
So, to get started, Jesse's going to give you a brief overview on GoProto, and then we'll go straight into the topic for today. So, Jesse?
Great. Thank you very much for the introduction, Kristen. Appreciate it. And again, thank you everyone who's attending this webinar. We've got about an hour. Kristen's going to go through the agenda here in a little bit, but we'll spend a few minutes on each slide. And again, just a reminder, this is kind of a chat office hours type of structure to this. We're not just going to show a bunch of PowerPoints as the main content. It will be used as kind of an outline format. So what we wanted to start with here is talking just a brief bit about GoProto and why we are worth listening to for your product development and analysis between today's subject, which is 3D printing and injection molding. So we wanted to start off with this graphic here, just showing that we produce projects all the way from concept models or ideas into production, all the way through the whole continuum from beginning to end. So turning your ideas into reality. So what we wanted to talk about, what that means is we start off with concept models. Those are machined or 3D printed early design studies that will be painted and graphics applied and so on to make early proof of concept if they're a cosmetic, or if you're doing early testing on a fixture or testing on parts, we'll make early concept models. We also, of course, do 3D printing. That's a big subject of today, and we'll talk through the technologies that we're utilizing here in a little bit. It's a very important part of this presentation here today. Urethane castings are an important step that can be used as kind of a bridge solution, and we do that process very well. That is where you would make a master pattern using either 3D printing or machining, and then a silicone rubber tool, and then cast multiples in that silicone rubber tool. And that can be used for casting color and texture, elastomers, overmolds, and simulations to injection molded parts. So very important kind of bridge early prototyping technology. Then CNC machining is a major focus of our company. We do plastic and metal machining. We do low to high volume, as well as different types of techniques to achieve different tolerances depending on what you're looking for. So that's a strong suit, something important to keep in mind, because we're not always just advocating 3D printing. We really also look at more conventional technologies. And then, of course, tooling and molding, and that speaks to injection molding tooling and injection molding, and those are of polymer parts. So we use metal tooling and then polymer injection molding, which we'll be speaking about today. And we do that from early concept or early trial kinds of tools all the way through high volume production, class 101, multi-cavity hardened steel tools. So we'll talk about the differences in that today too. Then sheet metal is a big part. You know, a lot of times plastic is assembled to sheet metal to form chassis, sub-assemblies, that are going to have plastic enclosures on them and so on. And so we have a little picture there just showing sheet metal we do from onesie twosies up to higher quantity too. So important to know that we understand that part of product development. Then we'll speak today a lot about additive manufacturing, which is just another term for higher volume 3D printing. That is where you would 3D print your production parts. And so we'll be talking a lot about additive manufacturing. That's a big focus. And that basically just takes 3D printing, applies a lot of the ecosystem that's around injection molding for quality and design analysis and so on into 3D printing to yield additive manufacturing. And then very importantly, finishing. You know, you can 3D print parts that are great. You can machine parts, you can injection mold parts, you can make concept models, you know, but you finish them. They need to be painted, they need to have graphics applied, they need to have different kinds of inspection done, and that's included in the finishing. And it's a big part of our company. We understand taking your product all the way to the final details, which are going to make it usable. So that's just a brief rundown of GoProto. So Kristen, I believe.
Okay, great. Thanks, Jesse.
Sure.
So to get things started, we thought we'd kind of jump right into what you guys, what kind of questions you've submitted. So when you registered for this event, we asked you to each submit a question that you'd specifically like answered. And what we've done is we've taken those questions and crafted the conversation today, hoping that we can address all of those questions. This is a bit of a representation of the questions that everyone submitted. Obviously, there's quite a bit of requests to discuss the selection criteria between 3D printing and injection molding, just in general. Also, the break-even points between, you know, as it pertains to cost and volumes, the materials, how they differ, and quality concerns like resolution and tolerances, amongst other things. So what we did is we took all of the questions and grouped them into categories. And so these are the categories that we're going to cover today. Hopefully, the intention is to cover all the questions that you put as you registered, but we are allowing time after each section to answer specific live questions. So you should be able to see at the bottom of your screen, there's an option for a Q&A. So you can click in there and you can submit a question on any given topic as we go through them. And I'll keep an eye on the Q&A and we'll try to address those questions at the end of each section. There's also an option, you should be able to upvote other people's questions. So if you see a question that you particularly want to have answered, that's an opportunity for you to upvote that question and hopefully then it'll bump it up in priority. So to get started, we'll start with the 3D printing technologies. A lot of people actually ask just for kind of a basic overview in terms of what kind of 3D printing technologies we're going to be discussing and how they compare to injection molding. So we are. So Jesse, I think you want to go through this?
Sure, yeah. Again, I want to encourage anyone who has any questions to pop them into Q&A. The point of today is just to discuss it. Jonathan and Mark and I will be kind of discussing ideas here, and as we talk, different ideas will come up, and if you pop in questions, then we can adapt. The idea here is to have this be a discussion. So what we wanted to look at or discuss with you were the different, you know, there's kind of 5 primary technologies that are generally commercially most prevalent. So we'll kind of go through those. I'm going to start with the bookends. Multi-jet fusion and SLS are both, you see the little yellow thing, they're powder bed technologies. They start with granulated polymer. You notice we're also talking about elastomers. So again, or excuse me, polymers. So today, again, remember that we're focusing mostly on polymers. Of course, we do machined metal, sheet metal, additive metal, and some die casting, but the focus of today's conversation is on polymer additive. So let's talk about multi-jet fusion and SLS that are both powder bed technologies. One of them, multi-jet fusion, a little graphic there shows that it's a droplet-based technology that applies drops of agents to a surface in a cross-sectional shape of the part. High intensity light passes over, and wherever those drops have been applied, it absorbs enough heat to sinter the material together, to melt it, to bond together. Whereas selective laser sintering, or on the right there, is a laser-based technology that wherever the laser strikes the surface of the powdered material, it melts it together. There are some fundamental architectural advantages that multi-jet fusion has over SLS. SLS has some material advantages, has some materials that MJF hasn't quite caught up on yet. It's a little slower. Multi-jet fusion is much faster in printing, creates more dense parts. This process, multi-jet fusion, we had in-house. it's a strong investment that we've made because it has so much power with higher quantities. It has highly dense parts, so it creates parts that are very much like injection molding. So the nature of the conversation today of exploring when would you use 3D printing versus use injection molding, multi-jet fusion has really changed that equation a lot. So our conversation today would be different than it would be just 3 years ago prior to its advent into the commercial space. So that's an exciting technology that we want to talk about and we'll be kind of analyzing in detail today. Then fused deposition modeling, this technology has been around for a long time. It's a filament-based technology. You see the little graphic there where you've got filament in a spool. It's fed up through the machine. It goes through a heated extrusion tip, and then molten material comes out and is laid down in the cross-sectional shape of the part, layer by layer. The platform drops down, or the print also can go up to the printer, and this is formed. FDM is interesting, has been in widely adopted use because it prints parts in production grade material or production materials. And it's got a wide range, everything from just basic general purpose ASA or ABS material into specialized materials like Ultem and PEEK and carbon filled materials, both chopped carbon and continuous strand. So FDM is interesting. It's and in wide use. Most college students come out with an FDM printer. A lot of companies have them in-house. They're inexpensive or can be up to high quality commercial printers that are more expensive and fast. But it is still a relatively slow process as its major kind of drawback. It also has got fairly low tolerances. A lot of you asked about what are the tolerances. It tends to be a little lower than some of the other technologies. It also is quite non-isotropic, meaning that the layers are laid down and the adhesion from layer to layer isn't as great as it is with the other technologies. So if you have a housing with a clip standing up or a boss standing up in the Z direction, the layers can come delaminated and you can have quite a weak part, even though the material is strong. It's the bonding between layers that causes some problems. So it's a tool to be understood and used, and we can help you through the analysis of that process. Then stereolithography. This technology has been around since the early 90s. I mentioned in my bio that I worked on the early 90s on the iMac and so on. This technology was around then. It's been around for a long time. It has advanced. Just like computers, the processors have gotten faster, the mechanisms have gotten faster and better, the lasers are more precise, the sweeper is better, but it is still fairly slow, and on its at its core, it is still a photopolymer process. So you still have a material that cures by laser, and then continues curing over time. So you end up with parts that become yellow, parts that become brittle after a couple of weeks to a few weeks, to sometimes depends on what you cook them with. So it's been primarily used as a form fit, check it out, prototype technology. DLP or digital light processing, some of you may be familiar with. It's similar to SLA. It's flipped over. It's faster because it's light rather than a laser. And it has some advantages over SLA. Like I mentioned, it's much faster. It has some really nice materials, including some elastomers that are okay. But again, they're all photopolymers, and so they're, as they get used in production, sometimes people discover limitations that make it not really the best for full volume production. So each one of these should be considered like a tool in your toolbox. They all kind of have pluses and minuses. We're here to help you kind of go through and analyze which one might be the best for your project. So really understanding what your needs are is a critical part of choosing which technology to use. We wanted to emphasize that we pull from different machine suppliers, so we're technology agnostic. We can really truly analyze your project and your product and your part and help you figure out what is the best way, and then help analyze it on the continuum of your product development to figure out when might you deploy it, and we'll go into that in later slides. Kristen, you're still muted.
Yep. So Jesse, just so you know, it sounds like we're having a little bit of issue on your end regarding sound. So I turned off your video, and that does seem to have helped, but if there's anything else you can do, that might be a good thing to look into.
Okay,
in the meantime, we'll move on.
Okay.
To the next topic. Does anyone have any questions on regarding 3D printing technologies in general?
Especially if you couldn't hear me, it might be a good time. Jonathan or Mark, did you have anything that, because you couldn't hear me, you might want to fill in with?
No, I think I'm good. Unfortunately, Mark's not going to be able to join us, it sounds like, or he might be able to come late because he got tied up with a few other things.
Okay, well, moving on then, we'll move on to volume and cost. I think this was definitely a big topic for a lot of people in terms of the break-even points and what kind of volume considerations to keep in mind, how do the costs compare, and how do the material usage and corresponding costs compare, and how are they different? So, Jonathan, do you want to go ahead and start with this one?
Sure, yeah, I'll jump in. So one thing to keep in mind as we go through all of these slides, when you're comparing 3D printing or additive manufacturing to injection molding, is the environment that the parts are going to be used in, how the parts are going to be used, and what are the requirements. So just keep that in mind, because that comes into play with the answering a lot of these questions. So what are the volume considerations? As far as volume goes, what you typically have found in the past, and really now, is 3D printing or additive manufacturing works well for lower volume applications. Let's say you got a project and you got a set of parts at 5,000–10,000 a year, and it's got a short product life cycle and you just can't justify the tooling. That's where 3D printing or additive manufacturing really comes into play. Then how do costs compare? Costs that's a loaded question, quite frankly, and a lot of these are really good, but we could spend an hour on each one of these slides we're going to go through today, so we're trying to sort of hit the high points. When it comes to cost, you have to think about, from a standpoint with injection molding, you have a capital expenditure cost for the tooling, whereas with 3D printing, you do not. So when you roll all that in, a lot of times you'll find when you first quote projects, 3D printing parts, the actual individual part is more expensive than the actual part cost for injection molding. But then when you start rolling in the cost of the tooling, you'll find that it'll be a lot closer to the 3D printed part cost. Sometimes the actual cost could be even higher than a 3D printed part cost. Once again, it depends on the part, depends on the geometry, and depends on what you're trying to achieve with that actual part when it comes to cost. And then as far as material usage and corresponding costs, how are they different? Materials, what you find with materials is, in the 3D printing world, the process dictates the materials that you can use. So in the injection molding world, you're wide open on the kind of materials you can use. Obviously, whatever the tool can handle is the kind of materials that are available. There's thousands of different engineering molding resins you can use, whereas with 3D printing, there's only a handful. Material usage, each process in the 3D printing world utilizes and uses materials in a different fashion. The powder bed technologies that are thermal based, you have the part material that is used to actually create the part, but then on the exterior of the part that's sort of surrounding the box, if you will, where the part is being made, there is heat that radiates that you can't really reuse 100% of that. We can reuse about 70 to 80%, but not 100%. And then the corresponding cost, it really breaks down to part volume and, what all is incorporated in that part. Hopefully that answers questions.
Yeah, we also, I think, we have a chart here that I think maybe, Jesse, did you want to maybe add?
Sure, yeah. Is my speaker working okay? I kind of clicked around on, okay, good.
You sound good so far.
Yeah, good. So there were some questions on break-even analysis, and this is an example of one we did on a small part. Something to consider here is that when we talk about cost comparisons, we are considering parts that can be injection molded. Part of the equation here will change around a lot if you enter in things like whether or not a part can be molded. If you take advantage of 3D printing or additive manufacturing and do things like adding lattices or adding combined components, things that are interlocked, things like that that you can't injection mold, then this equation dramatically changes. But if you have a design that's, let's call it a fairly small part, something palm size or smaller, can be molded, can be 3D printed well, and so all you're considering is cost, you could look at something like what we have charted here, which shows that if looking at the different lines, we've got MJF, we have MJF smooth, which is something we'll talk about. That's a post-process vapor chemical solvent process where the MJF parts are exposed to the solvent in a controlled machine that ends up completely cleaning it so they come out clean. It makes the parts smoother and a little bit more production friendly. Certainly makes them stronger. So we added that because it does add cost. So you see that on the left side, you've got no tooling cost for MJF, for multi-jet fusion, whereas you do with injection molding. With injection molding, you don't get parts for a while you make the tool, whereas with injection molding, or excuse me, 3D printing, MJF, you get parts right away. But then they start to cross over at a fairly lowish quantity in this particular example, somewhere around 450 or a couple thousand, kind of somewhere in that ballpark. Again, not considering time because multi-jet fusion is way faster to start. But you get a crossover and you see that pretty quickly injection molding actually in this particular example makes a lot more sense. This has been something we've analyzed closely with PPE in the recent past, looking at face masks and face shields and ventilator parts and so on. This has been an analysis that we've done, and we have found that injection molding catches up kind of quickly. But again, then you're locked out of all of the advantages that 3D printing brings. So this is one way to analyze it. It's just looking at cost.
Yeah, we just had one, Jesse, I'm gonna jump in there real quick. We just had one question come up, and the question was, are you FDM printing metal molds to reduce tooling costs? This is, very good question. This is something that has been discussed over many years now. And the first part of your question, FDM, I'm assuming you mean like some of the new metal extrusion based machines. You can't obviously, you could FDM a plastic mold and shoot maybe 100 parts into it. But the challenge with molding plastic into plastic from a cooling standpoint and just getting good quality parts off the tool is a challenge. Not only that, having the plastic part being able to hold a clamp force in a press to be able to get good parts. So you have really two things there that have been discussed over the years is printing plastic molds to mold plastic parts where you can maybe get 50 or 100 parts off of it. And that doesn't really work well, or printing metal molds out of like a DMLS system. The problem with doing that is the tooling costs can be extremely expensive because metal printing, direct metal laser sintering processes is very expensive. So when you start looking at the cost, you really are better off by just machining the tool from scratch. Now, one thing that, and I don't want to go too far down a rabbit hole, but one thing that DMLS is starting to do to help reduce cooling times, part warp, it increases time on, or it speeds up molding time, is actually 3D printing conformal cooling inserts that you can put into tools. But that's a totally different discussion.
Yeah, there is also the idea of, like you said, Jonathan, like clamping force and so on, like the parting line around a tool and the smoothness of the core and cavity to allow a part to eject is challenged with 3D printed mold inserts. And so you often end up then needing to post machine them to find the datums and find zero and make a nice smooth surface. And by the time you do all that, it's often more cost effective and certainly a more predictable outcome to just machine it from the beginning. So we've, as a company, focused very hard on just taking traditional technologies and making them really fast by advancements in mold-based technologies and advancements in our CAD, CAM tools, and really just continually learning how to make things faster and faster. So that's kind of been our general focus, although we've always got our eyes on the ability to 3D print tools, because like Jonathan said, you do come up with things like conformal cooling and things like that that are very interesting for injection molding. Kristen, can you try, if my audio is working okay, can you turn
your audio's, your audio's moving fine.
Oh, great. Can you turn my video back on when you get a chance?
Yeah.
Okay, great.
So we're going to move forward because we have quite a few topics still to get through, and we're already starting to get behind because there's a lot to talk about. We do have a question here for medical grade materials. We will get to that in the materials section, which is coming up. So hold that thought, and if we don't, I'm sure Jesse or Jonathan can address it. In the meantime, we're going to move on to injection tooling, the various types of injection tooling, and how they compare to 3D printing.
Yeah, so this is really the three areas that you see for tooling, really with our company or tooling in general: rapid injection tooling, bridge tooling, production tooling. And we play in all three of these sandboxes, if you will. The rapid injection tooling is going to be more of a soft steel or an aluminum tool where you're going to run 500 parts and be done with a tool, strictly a prototype, or you're going to do very low volume applications, say 5,000 to 10,000 max off that tool. The second one is a bridge tooling scenario where your lead time, as you can see there, can be a little bit longer, can typically range in around the 4 to 5 week range to get the tools completed and T1s off of it. This is, in my opinion, this is where we really shine as GoProto, because our bridge tooling, if you will, is fast and can be used as prototype tools. It can also be used for low volume production tooling, where you have a product life cycle that is very short and you just can't justify a, say, 16 cavity tool that's going to take you, I don't know, 2 months to produce T1s off of it. So bridge tooling works really well for not only low volume production, possibly even some prototypes, and then bridging that gap, of course, between prototype world and high volume production. And then you have the last one there, which is production tooling, which can be 4 to 8 weeks, sometimes even longer, 12, 16 weeks, depending on the cavitation that's required, the volume that's required, one thing after another. And that's where you're going to be making a tool there that's going to run a minimum of 100,000 parts. More likely, you're going to see 500,000 to 1 million parts off that tool. That's where the production tool area really comes into play. And it's going to be hardened steel, and you're going to have a lot of action, sliders, lifters, that kind of thing. And then how these go ahead, Jesse.
Sorry, I was just going to pipe in with that, like just real quickly, that we can do slides and lifters for all of these. So undercuts in your parts we're capable of doing that in all of these. Another key thing, answering part of the question that was asked a minute ago, is medical materials. Some of those medical materials that need to be autoclaved are higher temperature. And so to process a higher temperature part, you need higher quality steel or hard steel. And so that tends to be something more if you're going to be, say, running Ultem or one of the other medical materials, maybe a liquid crystal polymer, one of the filled materials. You may need tools that are, say, in NAC 80 or one of the harder steels like H13 or S7. Those are going to tend to be in bridge or production tooling. So you'll only be able to use kind of some of these tools depending on what you want to do. And then Jonathan, you were going to say.
Yeah, one thing to keep in mind too for the rapid injection tooling or even bridge tooling, to help keep tooling costs down, one thing that is an option to do is being able to do hand-loaded inserts, where it's like a jigsaw puzzle, mold a part and you pull it out and you unscrew, say for a thread, you unscrew that part of the tool, put it back in the tool and remold the part. Now what that does is makes your tooling costs cheaper, but it increases your part cost because you have a little more labor time involved in it. But if it's a low volume application and you want to keep your tooling costs down, that's really something to keep in mind. And then how do these compare to 3D printing? Once again, 3D printing is going to live in that world of rapid injection tooling or bridge tooling. You're not really going to use 3D printing when you're starting to look at high volume tooling applications where you're doing ink pens or razors or whatever. They're doing millions of parts off those tools annually. Once again, you got to keep in mind that with 3D printing, you don't have the tooling costs. So your part cost is going to be a little bit cheaper, but you don't have that capital expenditure that you have to come up with. And then your design freedom, which we'll get into later as well, is greatly increased, and you can do a lot of customization on parts, which is a big topic in the world right now of not only auto manufacturers, but your consumer appliances, consumer products, you name it. Everybody wants to somehow customize it.
Great. So just if you're curious, I mean, this is obviously kind of difficult to see maybe on some of your screens. So just so you know, we will be emailing this comparison chart and another comparison chart that's similar that compares 3D printing and injection molding out after this webinar. So don't worry about it. If you can't see it now, you will later. So one question just came up on the topic. What about production tooling using 3D printing for providing unique geometries that can't be machined by traditional means?
Yes, that could be that's something like you may be able to say 3D print a section of a tool that you could then insert into the tool, maybe to interchange. There's often an injection mold tool will be made with a pocket that you can then insert different inserts into, and that would be done for, say, if you wanted to brand for different customers, if you wanted to have a different part number, if you wanted to have a different feature on a part that allows it to do something else. And we could potentially machine the majority of the tool or EDM the majority of the tool, and then 3D print sections and put them in. And we have done that. That allows for some differing, as the questioner just mentioned, kind of different geometries that are difficult to machine. And we have done that, though it is kind of still early, and it ends up being something that is a kind of fairly limited benefit. It has to be a very specific application. Did I interpret that question right, Jonathan? Would you agree with this?
Yeah, I would definitely agree with that. Yeah, it's a very it has to be a special scenario to be able to do that.
Right. Yeah. Yeah, and I would think, say geometric textures and things that might be, if you've got a cosmetic area where you have something. I have a sample part. I don't know how well you can see, but things that are non-animal textures, so like diamond plate and snake belly, and you can do some different textures that you might be able to then install in the tool. So that could potentially be done.
Okay, so moving on to the next topic, we have materials. We have the questions here that were submitted ahead of time, but then we also had a couple people interested in finding out if we can print medical grade materials. So if you want to address that as well.
Yep.
Jonathan, do you want to start?
Yeah, sure. I'll address the medical grade first. There are some medical grade materials out there. One of the things about medical that is a lot of people want to be able to do is sterilize them. So with the PA12 material that runs in the MJF technology, you can sterilize them through an autoclave process. And it does have some FDA clearances for skin contact type devices. Is it an implantable? No, not necessarily. Then there are other medical grade materials out there as well. There are some for the SLA technology. There are some for the DLP technology. There's none for the PolyJet technology that I'm aware of. There are medical grade materials for the FDM technology as well, but it's few and far between. One of the things, and I mentioned this earlier, one of the things to keep in mind with the FDM, with the 3D printing or additive manufacturing world, is the process dictates the material you can run. So if you're going to run nylon 12, you're going to have to run it in a heat bed technology, or you're going to have to run it in the extrusion-based FDM technology. FDM does have actual engineered resins that is extrusion-based, but the quality of and the resolution of the prints are challenging. But you can run PCABS, you can run ABS, you can run Ultem. What else? Jesse, am I missing? ASA for
yeah, and FDM, carbon filled material.
Yep, PPS.
Right.
And that's an FDM. And if you're as you're looking at your screen, that gold looking part, that's an Ultem printed FDM part. And then in the
there's two kinds of Ultem. There's 9085 and 1010 run on the Stratasys machines. And they have different medical capabilities.
Exactly. And then on the powder bed technology, the MJF and or the SLS technology, you're all going to run nylon-based, polyamide based materials. Majority of it is nylon 12 or nylon 12 with a glass bead. There is a nylon 11 out there as well that is a great material, and there's some elastomers coming on board. When it comes to the SLA world, stereolithography, or the DLP, it's all photopolymers. So it's nothing that is actually engineered resins. It is something that is going to be similar to an actual engineered molding resin. So What that means is that you're not going to want to use it for any type of mechanical testing. It's more for show models. You can paint them to look exactly like you want a injection molded part to look, customer samples, internal in-house samples, engineering review samples, that kind of thing. But they are brittle. They'll crack, they'll fracture, that kind of thing pretty easily. And then how do high temperature material options compare? There's only a few in the additive world compared to the injection molding world. Once again, the injection molding world, you have hundreds and hundreds and hundreds and thousands of options of resins for molding parts. In the in the additive manufacturing world, you have high temperature material in the FDM, which is PPS and Ultem. And then you can consider nylon as well as a high temperature material because its heat deflection is about 173 C, so that's about 350 Fahrenheit, and that's in the MJF technology. So you really only have a handful in the additive world, whereas in the injection molding world you have all kinds of options.
Yeah, there are some peak and peck options too, if folks online are familiar with that, but they're just not as widely used. They take some more adaptations to the machines. There is an Antero material that I believe is a PEC-based material that we're able to run on the Stratus machine, kind of similar to the gold part in the picture there. So there are some, but like Jonathan said, it's a handful, not like injection molded.
Yep.
So we have one quick question, I think, on this one that we'll put into this category. Even though it's about a printer technology, I think it's really a materials kind of question, is which 3D printed technology would be used when a part will undergo heat cycling but not much mechanical stress? It's low volume since the total quantity would be under 1,000 parts.
Jesse, I'll jump in on that one.
Sure.
It really depends on what type of heat it's going to see. You know, if you're just putting it maybe in a wind tunnel type test, I would run like the FDM Ultem material because it'll handle it. If you're just if the part's just gonna sit static and it's gonna see heat that's, you know, less than 175 C, you could go with the MJF nylon option. So it really depends on the kind of heat that the part's gonna see on what materials will be available for that particular application.
And that kind of quantity is a good one that additives should work just great. And we've had some, you know, I mentioned that some new options are available with multi-jet fusion and some of the other materials as well. We have had clients that have taken MJF parts and taken them up to temperature and back, you know, in cycles over and over, and it's performed remarkably well. It's a lot like it is production nylon.
Yep.
Perfect. All right, so we'll move on to the next topic, which is quality. How does feature resolution compare? How about the tolerances, and which one makes sense when the costs break even?
Sounds good. Real quickly, we've got about 20 minutes left in the presentation. We've got those three and some Q&A, so we'll try to kind of move quickly, though these are very important topics. So,
yep. So feature resolution, you can get good quality features out of the 3D printing technology, but once again, each process has its limitations on feature resolution. The SLA is the best. It's the granddaddy of all the additive technologies. It was developed back in the mid-80s. It cures the material with a laser, and you can get very fine details on that. You can get down to feature resolutions and tolerances of 1 thou. So it's the best when it comes to feature resolution, but you're going to sacrifice mechanical quality. FDM, I would say, which is the extrusion-based technology, is on the other side of the spectrum, where it has the worst feature resolution because it is an extrusion-based technology, and you really are not going to want to go much less than, say, 10, 15 thousandths on features. Maybe you probably even be better off going at 20, just so you know they come out in good quality. So it's on the other end of the spectrum. And then sort of in the middle, I would say, and Jesse, you jump in here if you think different, I would say the multi-jet fusion is sort of in the middle because you can get 5 to 7 thousandths as far as feature resolution, and tolerances on the MJF technology, which is getting closer to your standard, you know, sort of rule of thumb injection molding tolerances, but not quite as good as SLA.
Yeah, so thanks for the invitation to jump in. I'll take it. Just real quickly, we'll talk about on the next slide here, part properties and design, and feature resolution and tolerance play very much into part design. You can expect that if you design the part well for additive manufacturing, you're going to get a part that comes out well. If you're designing something just for machining, it's a manifold, say, and you've got a big block and you expect the diameters to come out well in a 3D printed part, you may not achieve the tolerances that you want. Whereas if you lightweight it and core it out, you're going to get much better tolerances. So the answer depends a lot on everything from orientation, part design, and materials chosen, as well as, of course, technology. So the answer varies around quite a bit.
Yeah, and then the last question here: which one makes sense when costs break even? It depends on the application.
Yeah.
All of these slides, it really depends on. You got to evaluate the application. Is the materials that are available for additive, are they going to work for your needs? 1, 2. 2 will be, is the kind of quality, surface quality you're going to get off the parts once they're printed, will that meet your needs? Do you have to have certain texture that we can't achieve, for instance, in the additive world, but you can't achieve it in the injection molding world? Are you going to require some type of clear lens that is insert molded into a plastic PC part? You can't do that in the additive world, but you can do that in the injection molding world. Are you going to require some type of overmold or soft touch? You can't do that in the additive world. You can do that in the injection molding world. So once again, you really have to evaluate what the application is going to be on which one makes more sense.
Great. So I think on that note, we'll move on to the next topic, part properties and design.
Sounds great. Excellent. Again, this is Jesse. I'll address this one. Part properties and design has a massive impact on most of the other slides that we've talked about, on which process the part is a good fit for, what your part costs are, what your tolerances are, what you can expect for surface finish. And the answer, well, how do I design my part to be the best for all, is going to vary on the technologies that you use. 3D printing is exciting because you can use different design criteria to design your part, and you can do things that you don't have to worry about with, or that cause problems with injection molding. We've all had problems with things like draft, which is the angle that you need to allow a part to be ejected off a mold without sticking. You don't have to worry about that with 3D printing. You can have, in injection molding, you need to have what are called consistent wall thicknesses, meaning that you can't have a rib that goes into a wall and have it be too thick and create a sink, because you've got a big kind of ball of wall thickness where the rib meets the nominal wall. You don't really have to worry about that as much with 3D printing. But with 3D printing, you can, if you design a part well, you need to consider things like nesting. Nesting in a powder bed technology is think of like Tetris, where you're trying to fit all your parts together in a way that they are the most space efficient. And your part design, if you have let's say a boss that's sticking up, and that prevents other parts from nesting around it, then you're going to have fewer parts than you can print per build. You're going to have a higher part cost. You may also have tolerance issues or some other problem like that. Whereas if you say make that as a separate piece, or you combine it, or just change where that feature is, you may be able to then nest your parts together better. So design is as important, if not more important than ever, because you can use your technology as well. Now, with 3D printing, it's got some advantages that you can get away with some things. You don't have to worry, like I said, about draft or wall thickness in the same way. So it's how part design is interpreted is going to depend on the process that you're using. So looking at the questions that were submitted beforehand, what do we need to keep in mind regarding part design? We've got a lot of registrants from different industries, and the answer is going to be, it kind of depends, like Jonathan just said, on your application, on your industry, what you're trying to achieve, and which technology you want to use. And again, we can help kind of counsel through that. You see, we've just got a graphic here showing some mold flow. We do use software to analyze everything from 3D printing nesting to feature resolution. If a feature is too thin, we can look at that feature, talk it over with you, figure out how we might be able to re-engineer that part to work for the process better. With mold flow and on into the injection molding side, looking at how's material going to flow through the tool. Are there things that we can do to modify it to help it run better, to achieve better quality, or faster, so that you get lower part cost, so on. It's part design is massive. There are also things that what do we need to keep in mind regarding part design? I don't know if you can see, or if everybody's looking at their screen, but this is a 3D printed part that has got texture printed into it. I showed it earlier on the back side. You can see those a little better. One side is an animal grain leatherette. The other is geometric texturing. Geometric texturing is something that's really difficult to do in injection molding, because you've got to figure out how to etch the tool or machine it, and you can 3D print really incredibly complex texture that you might not even be able to make with injection molding. You can also, this is a little interlocking cube that we have as a sample part that's 3D printed. This is something that this concept of interlock parts, eliminating fasteners, eliminating adhesives, eliminating assembly steps, reducing the number of people you need to have on the assembly line or the possible issues. There's massive advantage that you can take. But a problem is that a lot of us are not used to designing parts thinking about that, because the 3D printing technologies that we've been able to use in the past haven't been good enough to make parts that are production worthy. And now you can, so it's changing it a lot. So it's pushing us all to think outside of our traditional 3D boxes. So it's a very exciting time to be a part designer, but there are a lot of options and we can help you through it. How do the mechanical properties differ between, I'm gonna take that in the frame of, say, nylon parts, injection molded nylon parts versus 3D printed parts. Something that's important, another advantage here is the idea of isotropic versus non-isotropic mechanical properties. The 3D printing technologies, I mentioned it earlier when we were talking through them, all have different isotropic or non-isotropic properties. That's how much the layers stick together and what the mechanical properties vary, whether you're in the X and Y or the tall direction, which is the Z direction. SLS is pretty good at non-isotropic or on-isotropic. SLA is actually pretty good. FDM is not good at that. DLP is okay. MJF is very, multi-jet fusion is exciting in that it's quite isotropic. It is going to perform very similarly in the Z as it does in the X and Y, which is another reason why we've adopted it. So again, if you print a flat bezel and you've got a tall feature here, you can expect it to perform a lot like an injection molded part. That also comes into play with secondary processes. If you're doing things like heat staking or some other assembly process that you need the 3D printed material to perform like your injection molded material, well, you can expect that to be the case with MJF. Injection molded parts, you're going to have molecular flow that allows the parts to be fully up to the mechanical standard you would expect. Say glass bead, glass filled material, there is a glass bead filled multi-jet fusion material, but it's beads rather than long fibers, so they don't lock together as well, so you don't get the stiffness that you would out of an injection molded material. So there are a lot of things to consider, and they do differ. But I'll move on quickly here. How does post-processing compare? I guess I kind of already addressed that a little bit, that we can do a lot with, say, multi-jet fusion, FDM, and SLS to some degree, with some things like heat staking, ultrasonic welding, applications of metal. If you needed a metal coated part, we can do that quite well. We've been able to apply Cerakote, which is a high temperature kind of a dry applied coating to multi-jet fusion parts that takes post-baking, and that adds the ability to have UV stability and high temperature as well as chemical resistance. So it's exciting because we can do more to it than we have been able to do in the past.
So we do have one question, Jesse. We have one more topic after this on the product life cycle.
Yep.
So there's a lot of time for that, but we have one quick question on this topic. What's the size of the batch in the case of nesting multiple parts to gain the cost advantage? I assume different designs of parts can be batched together if they are made using the same technology.
Yes, that's right. So that's the idea of what we call a Kanban basket, which is that, let's say your assembly takes 10 different plastic parts. You can nest them all together to make them in batches or sets at least in multi-jet fusion. You can do them in all of them. More so in a powder bed technology, because you've got this third dimension. With SLA or Objet or with the DLP technologies, you have to have sight from the part to the build bed. And so that means you can't stack parts. So MJF, you can stack them well. So that's a big influence on this in terms of lead time, because if we can produce more parts because they're nested together better, also because you're nesting better, you're better using the build, and you're going to experience lower part costs. So has a big impact. Does that answer that question?
I want to jump in there real quick to add to that, and I'll make it quick, Kristen. To add to that, from a nesting standpoint, the MJF technology, or any powder bed technology for that matter, the raw material supports the layers as they're being built. So right. You don't have to have a secondary support structure, so we can just take parts and just cram them as best we can to get good quality out of, say, that box, your building box dimensions. Whereas with FDM and SLA and PolyJet, they have to have a secondary support structure because they the first 200 thousandths is nothing but support adhering to the build plate, and then you start building on top of that. So you can't build on top of other parts, because then you have to have a support structure to continue to build it.
You bring up a very, very good point, Jonathan. And that is with part design, that with a powdered bed technology, you don't have to worry about supports going from the different members of a part. So you can do things like lattices, where you can just remove the powder and then you end up with a part that's interchanged. Whereas if there were supports in here, you wouldn't be able to reach them to get out of them. Also, you don't have a sacrificial surface. So, well, I'll show this part again. If we had this in SLA, you would have supports all on the bottom side here, and when you remove them, you would end up destroying the texture. So you'd have one good side and one bad side. Well, with 3D printing in powder bed technology, you can have texture on both sides because the powder can be removed and you don't end up damaging one of the surfaces. Huge.
We do have one more quick question I think we can squeeze in here that popped up related to design and post-processing.
Sure.
Do you add metal threaded inserts to MJF or other technologies as a post-process?
Yes.
Yeah.
So yeah, great point. So this is a thermoplastic. Thermoplastics, once the part is formed, they went from solid to liquid by heat and then back to solid. And so they can be turned back to liquid again. So when you're inserting a brass insert, you're heating up the material either by hand or by a machine, and then inserting it as the part is melted, and then the material solidifies back around the insert. With the photopolymer processes like SLA or DLP, it just kind of gets soft and sort of moves out of the way, and you sort of stick the insert in, but then you have to glue it because it doesn't get back around the knurling. With powder bed technologies, it does. It melts and gets back around the insert. So you can expect the inserts to perform a lot like they will with your injection molded part, if not exactly the same. And we've done some very specific testing on that, and it's come out excellently. So that's like, again, that makes it very, very capable of doing what you would expect out of a production part.
Yep.
Great, so we'll move on to the last topic here, product life cycle. Jonathan, do you want to go ahead?
Yeah, I'll jump in here and take this one. So the blue, as you can see, that we got three different colors: for yellow for injection molding, blue for additive manufacturing, and then the green sort of an overlap where those two technologies would come into play. The front end and then the back end of a product life cycle is where additive manufacturing traditionally has lived. The front end has been 90% of what the technology has been used for since the mid 80s. You know, you're doing onesie, twosie, 5, 10 parts for looking at different ideas, prototyping, that kind of thing. And then the end of it now is with MJF and other thermoplastics, you can start looking at replacing end of life tooling or, service parts that you don't want to pay for tooling for, or you no longer have the tooling. But it's getting to where you can start seeing in that middle area from bridge production to the end of the product life cycle, where additive manufacturing is starting to come more into play, where traditionally injection moldings come into play. But you still want to keep in mind the volumes that you're going to be going after on when you use a particular technology. Once again, if it's going to be a lower volume application, 5,000, 10,000, 15,000 parts a year, you really can look at doing additive manufacturing. But if you're going to start getting into that higher volume where you're going above 50,000, above 100,000, injection molding is still going to be your best bet. Unless you're trying to do a very specific application that has to require additive manufacturing. And the most prominent application out there right now that everybody is aware of is Smile Direct. They use the MJF printing technology for making the different arches for your teeth for the invisible braces, where they go, I think a patient goes through 5 different iterations, and all of those are patient specific. So they actually have to print what is basically the master pattern of each one of those stages in the MJF technology, and then they do their suck down process onto that master pattern to make the actual invisible braces. So, but that is a very select few cases in which that happens. It's not very common.
But just real quickly, John, I'll say, as there's, we looked at that break-even chart earlier in the presentation, and that just looked at cost and quantity. when you add in, there are many other things that each of you are considering. Like Jonathan just alluded to, you might have a short or very shortening product life cycle, or its usable window of time in the market. You may have part complexity. You may have a part that you don't really want to lock down design. You want to be able to iterate throughout the product life cycle. You may have things like tolerances that are a question, cosmetics, that could all change this curve. This curve here is just a generic, based on your quantity, kind of approximately where it might fit in. It could change depending on your application, and this curve has changed over time as well as the technologies improve. So go ahead, John.
A good example is we have a particular lighting customer we're working with right now that they have 4 different part numbers, and they're looking for this one particular product, and all they're going to need is 700 of each one of those on an annual basis. Before the MJF technology or the thermoplastic technology in the additive world came into reality, the only option they had really was injection molding it. And now that we have the multi-jet fusion technology with nylon 12 and its mechanical characteristics and what it can withstand from an ambient environment, they are really seriously considering the MJF technology for production of those parts. Now, once again, the individual part cost is going to be higher than if you buy a tool, but they don't have that capital expenditure for the tooling.
Great.
Great.
And
Well,
then,
oh, sorry, go on.
there was the one last question just to touch on it. Which should we use for prototyping? Really, your best bet still is 3D printing or the additive technologies for prototyping, as long as you can get the materials that you need and the materials will suffice for what you're trying to do in that prototyping phase.
Great. Well, we got 2 minutes if anyone's got any additional questions.
Well,
Alrighty then.
Okay, so I will say that as things change, as the technologies change, we're working very hard to keep up on it. We will continue to have other topics that come up. Some of the questions that have been posed here obviously lead to entire other webinars. So stay tuned. We'll talk about that. And then Kristen, you're gonna.
Yeah, and one other thing too, feel free to contact, you see our contact information there. Feel free to reach out to any one of us and email us or give us a call, and we'd be more than happy to talk to you just from, even if it's just from a consultative purpose, sorry, I can't speak, for your particular project. We'd be more than happy to discuss it with you.
Agreed.
Great. Well, there's one question that just popped up. Seems like finish accuracy has not been addressed regarding 3D printing.
Finish accuracy. Does that mean texture?
I think we're talking about post-processing.
Yeah. So post-processing, we work quite hard on. Multi-jet fusion, for example, makes parts that look like this. They're kind of matte gray, and that's an interesting start. But if you want to make them consistent black, we dye them. We work very hard on dye. You can add paint. You can add hydrographics. I mentioned Cerakote, and those, in terms of accuracy, those are all production quality finishes. They are production finishes. So we can make parts that are very highly finish accurate, we'll call it. There's also the finish accurate from the standpoint of tolerances, if that's what the questioner means, and that will depend on the build orientation, the material, the part design, the process we use. Sometimes they are accurate enough to be able to have the tolerance. Consider anything greater than plus or minus 5 is probably where these are going to play. Anything less than that, and we're going to need a secondary machine.
From a finish standpoint too, that we did not touch on, I'll touch on real quick. With the additive technologies, you can vacuum metallize parts, and you can also nickel plate parts as well, which not only gives you the cosmetics, but nickel plating will give you much increased mechanical properties of the part.
That's true. And then lastly, I mentioned back at the beginning of the presentation in the cost standpoint that we have vapor smoothing. So we have a machine that exposes parts to the solvents that smooths the surface, and that does 2 things: makes the parts look nicer, consistent, even, kind of semi-gloss finish, and then also it locks the molecules together, and so it improves elongation, so it makes the parts stronger, more heat resistant, actually better with chemical resistance, water resistance, and so on. So it's a multi-advantage process, and that is something that works very well with multi-jet fusion or FDM or even machine parts.
Question just came up. Does GoProto have a partner that will do the metallized coating? Yes, we do.
Nice timing, Jonathan just mentioned that. Yes, we do. Yeah, we can handle that.
Well, keep these questions in mind, and as Jesse touched on as well, this is just the first of the office hours that GoPro is planning on doing. So if you have any specific topics, and this is clearly, I think post-processing itself could be an entire hour, so we'll look into doing that as a potential topic going forward. Quickly answer the 3D printed to COVID. You can look at the medical page on goproto.com, and you can see where MJF has been implemented to create some PPE. The rest of these questions, if you want to submit any more, Jesse and Jonathan can certainly email you directly with some answers, or you can jot down their email addresses and reach out to them directly. So with that in mind, let us know if you have any other topics you'd like us to address in these office hours going forward.
Sounds great. We appreciate it, Kristen. We also will be in touch with the recorded, the link to the recorded presentation, so you can submit it to your colleagues or re-listen to it if you'd like to later. We will be in touch.
Great. Thanks, guys.
Thank you very much, everyone, for attending.
Thanks, everyone.